No Barbies were hurt in the making of this film.
You can't save her now.
Of course I can. I'm Bond. James Bond.
See ya when we...
Bond, you saved me!
Of course I did.
How'd you do it?
Easy. I just use a little something called calculus that my dear friend Miss Wood taught me.
So we know that the instantaneous acceleration is the derivative of velocity over time. If we multiply both sides by dt, and then take the integral of a dt with the bounds 0 to t, and then also take the integral of dv with the bounds v naught to v final. If we do out this integral, we'll see that the 0 cancels out, and we're left with a times t. Then, if we do out the integral for velocity, we get v final minus v naught, or v initial. If we bring over the initial velocity onto the other side of the equation, we are left with the equation final velocity equals initial velocity plus acceleration times time. Now that we have the first kinematics equation, we can use it to derive another. We know that the instantaneous velocity is equal to the derivative of the position in terms of time. Next, we can separate the variables again by multiplying each side by dt. Now we can plug in the equation we just derived for velocity. When we take the integral of the left side of the equation with bounds 0 and t, we are left with v naught t plus a t squared over 2. Then, when we do the integral of the right side of the equation with the bounds initial position to final position, we are left with final position minus initial position. Then, if you can condense the right side of the equation, you are left with change in position. For use in the real world, change in position can mean either change in x or change in y. Okay, Mr. Bond, so those are your kinematics equations.
So, now that you see how calculus connects to physics, we can use these two kinematics equations. When I saw that you were about to fall, I quickly estimated some calculations. Everybody knows that an average basketball hoop is approximately 1.83 meters, so I knew that this would be the vertical distance of your fall. I also noticed that I was about 1.2192 meters away from the bottom of the basketball hoop. I used the known information to evaluate your fall. I knew that you were only accelerating vertically due to gravity. I knew that the vertical distance was 1.83 meters, and I knew that you were initially at rest since you were dropped off the hoop. I used all of this information to solve for the time of your fall. When I plugged my estimates into the second formula we derived, I knew the time of your fall would be about 0.610 seconds.
Oh, I get it now. Because you knew that perpendicular vectors do not affect each other, the time it took for me to fall would be the same time it would take for you to reach me in your car. If you set up a want-no column for your horizontal trip, you knew that your horizontal change in position was approximately 1.2192 meters. Your initial horizontal velocity was 0 since you started from rest, and the time would be the same time from our first equation. Use this information to solve for acceleration. After doing these calculations, you came to the conclusion that you would have to accelerate at 6.5 meters per second squared to save me in time.
Righto, my dear. Now, let's head back to London.
This is the end. Hold your breath and count to 10. Feel the earth move and then hear my heart burn.
Because you knew that perpendicular vectors do not affect each other, the time it took for me to fall would be the same time would take. Damn it!
When I saw that you were about
After doing these calculations, you came to the conclusion. Oh, I don't know the acceleration yet, so I can't even do that part.
Swept away, I'm stoned.
Gotta love velocity and stuff.